So today we're going to start talking about Chapter 8, which covers sequences and series, which you've learned about in Algebra 1 and Algebra 2, just at least the basics and maybe how to find the formulas. We're going to start with a review today of Arithmetic Sequences, which is 8.1 in your textbook. Okay, so we're going to look at the sequence below with the different types of dots in it. So we're going to let Rn be the number of dots in a rectangular array, so that's how many dots are in each rectangle, that has n columns and n plus 1 rows. So if we look at the first one, we have 2 dots. The second one we have, which is 1 column and 2 rows. In the second box, we have 6 dots, which is 2 columns and 3 rows. The third, we have 12, so we have 3 columns and 4 rows. The fourth one, we have 4 columns and 5 rows. And our pattern continues. In the fifth one, we have 30 dots, which gives us 5 columns and 6 rows. So it says that we have n columns. So if we were to continue this pattern to create a formula for the nth term, we would want our r of n, our nth term of this rectangular array. So we can tell from the pattern so far that it's the number of columns, which is represented with n, times the number of rows, which is n plus 1. So this would be a sequence you could plug any number in for n and get a number out, and that pattern could keep on going forever. So for instance, if we were to do R6, we would know to do 6 columns and 7 rows, which would give us 42 total dots. I'm not actually going to draw it out, but you could if you want. So our formal definition for a sequence is a function whose domain is a set of consecutive integers greater than or equal to an integer k. So what does that mean? So a function is it's a formula, and our domain is a set of consecutive integers. So that could be like the numbers 1, 2, 3, 4, and so on. It could start at 2, so we can go 2, 3, 4. We could start at 10 for some reason and go 10, 11, 12, 13. So wherever we start, that's our integer k. So we have to start at a positive number and then continue to count up. So there are a lot of different famous sequences that you might actually be familiar with already. So one is your counting numbers. We have 1, 2, 3, 4, 5, 6, and so on. We have the sequence of triangular numbers, 1, 3, 6, 10, 15, 21, and so on. And then this one, the Fibonacci sequence, which is actually seen in a lot of different places in nature and in different artworks. So it goes 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on until we keep building up. And we're going to go over what type of pattern that is. So you can use series or sequences in your everyday life. So suppose you have $250 in your savings now, and you have a job, and you can save $75 each week. So we want to first create a list of the first 5 terms of our sequence, and we want to show our balance each week. So we'll let our balance be B. So at the end of the first week, we have $250. At the end of the second week, we've saved an additional 75, so we're going to add 75 to that. So 250 plus 75 gives me 325. So then at the end of my third week, again, I'm going to save an additional $75. So I'm going to keep adding on 75. So at the end of that, I would have $400. At the end of the fourth week, after saving an additional $75, I would then have $475. Whoops. And then at the end of my fifth week, again, by adding another $75, I would get $550 at the end of the fifth week. So say we wanted to figure out a formula to show how much money we're going to have given any week. So say we're looking forward and we want to know if we save for 10 weeks or whatever, how much money we're going to have in our savings account. So if we look at our pattern, we know our starting value, B1, is equal to $250. And then every week after that, we add on $75. So if we want to find the nth week, we want to take the prior week's balance and add $75 to it. So the way we would write this is, we would write this recursive formula. So we would say BN, so our balance at the end of the nth week. Well, if we're starting, we're going to say B1 is equal to $250. But if it's not the first week, we take the previous week, so that would be B to the n minus 1 subscript, because that would be the one right before n, and we're going to add 75. So this is called a recursive formula. And what a recursive formula is it just takes the previous value and uses that to find the next one. So everything is based off the value beforehand. So when we're talking about series or sequences, we have two different types of formulas. We have recursive formulas and explicit formulas. So we're going to just define what both of those are. A recursive formula gives you the first term or the first few terms. And then defines the rest of the terms based off of those terms. So what that means is, in order to find, like, say, the 50th term of a recursive formula, you actually have to find the 49th term, and the 48th term, and the 47th term. So you have to know the terms prior to the one that you want. So it kind of like works backwards, whereas an explicit formula is more like a function. So an explicit formula gives you a formula where you can substitute any value of n to find the nth term. So for instance, we can actually look at this function. So like 4 plus 6n, that would be an explicit formula because I could plug in the value of n and then tell you what the nth term of the sequence is going to be. Whereas the money problem that we just did on the previous slide is a recursive formula. I can't tell you the nth term until I know the term before it, bn minus 1. So the type of sequences that we're looking at in this section are arithmetic. So the formula for that, the theorem, whatever definition you want to call it, says let n be a positive integer and a1 and d be constants. So then the arithmetic sequence with the first term a1 and the constant difference d, so d stands for constant difference, can be described by the explicit formula a sub n is equal to a1, our first term, plus n minus 1 times d, or the recursive formula, which is stated below, which we always state in brackets. So we would be given the first term a1, and then our nth term is a n minus 1 plus d. So we have two different formulas that we want to know. So you're going to definitely want to write these down, and these you will have to know for your assessments. We're going to look at how we use those now. So in this example, we're given an arithmetic sequence with a sub 2 equaling 14 and a sub 6 equaling 4. So that means the second term in our sequence is 14. So say we have like a blank spot for a1, and then 14 is in spot 2, then 3, 4, 5, and the sixth spot would be 4. So we want to figure out a formula that is both explicit and recursive. So what we first have to do is we want to say, okay, if we have an explicit formula, we know in part A, our explicit formula is given by a sub n is equal to a1 plus n minus 1 times our constant difference. So if we look at the two terms we have, we know a2 and a6. So we know that a2, which is 14, has to equal a1 plus 2 minus 1 times our constant difference, which would give us 14 equals a1 plus d. And if we look at our sixth term, we know that 4 has to equal a1 plus 6 minus 1 times d, or 4 has to equal a1 plus 5 times d. So now we want to figure out a formula. So this is a system of equations, so I'm going to write them on top of each other. Okay, so I'm going to use what's called linear combination. So if you don't remember what that is, I'm just going to subtract the second equation from the first. So if I do 14 minus 4, I get 10. A1 minus A1, I get 0. And then d minus 5d, I get negative 4 times d. So this is really 10 equals negative 4d. If I divide both sides by 4, I get 2.5. So I get negative 2.5 is equal to my common difference. So that means I'm going down each time by 2.5. So in between each of my terms, I'm subtracting 2.5 to get to the next one. So I can now use that to work backwards to my first term. So I know I subtracted something minus 2.5 to get 14. So if I go backwards, I add, I get that my first term is really 16.5, which means my explicit formula AN has to be given by 16.5 plus n minus 1 times our constant difference of negative 2.5. Now we could leave it like that, but that's an easy equation to simplify, so we're going to go ahead and do that. So I'm going to get a sub n, my nth term, is equal to 16.5 plus distributing my negative 2.5, I get negative 2.5n plus 2.5. Combining my light terms, 16.5 and 2.5 gives me 19, so a sub n is going to be equal to 19 minus 2.5 times n. So that would be our explicit formula, and we could go ahead and check our work by plugging in 2 and 6 for n and making sure we got out 14 and 4 as our answers. So now we also had a part B here. So in part B, we wanted to write a recursive formula. So if we look back at our notes that we wrote down for what a recursive formula is, all you do is you take your a sub 1. So we know a1 is 16.5, and then our an term is equal to a sub n minus 1, and then you just add on your common difference. So for us, we're going to subtract that common difference of 2.5, and that would be our recursive formula. Okay, so for your OYO questions, you have a few questions from your book to do. I want you to complete numbers 5 through 8 and numbers 10 through 12 on page 507 in your textbook. So questions 5 through 8 are below for you, and then I'm going to go ahead on the next slide and give you questions 10 to 12 as well in case you don't have your book at home. So if you don't have your book at home, I would pause the slide now so that way you can write down the questions. Okay, and here are questions 10, 11, and 12. So if you get stuck, you can always refer to your textbook in section 8.1 for additional examples and some extra notes.